Welcome back, everyone. The ocean is essentially this massive, incredibly powerful, untapped battery. But to actually harness that wave energy conversion, we have to unlock a pretty fascinating mechanical mystery using the sheer power of computational fluid dynamics. Today, our explainer is diving deep into the modeling of an absolute marvel of engineering designed to capture that exact power, the Wells turbine. Right out of the gate, I want to pose this central paradox of this whole thing to you. Think about this for a second. How in the world do you spin a turbine in one direction when the wind is blowing in two completely different directions? Ocean waves constantly push and pull, right? They act kind of like a giant mechanical lung, literally inhaling and exhaling massive amounts of air. And yet, this highly specific turbine we're looking at today only rotates in a single direction. How is that even possible? Okay, let's dive into this. On our agenda today, we'll first unpack the wave energy paradox. Then, we'll decode the NACA blade aerodynamics. Third, we'll look at the computational fluid dynamics modeling. Fourth, simulating pressure and velocity. And finally, optimizing the Wells turbine's efficiency. Section 1, the wave energy paradox. Let's set the stage and look at the environment where this turbine actually lives. This brings us to a really cool concept called the Oscillating Water Column, or OWC. I want you to imagine a massive concrete chamber partially immersed in the ocean, just above the waterline. As the ocean waves naturally rise and fall, the water level inside that chamber oscillates right along with them. This continuous motion constantly compresses and decompresses the trapped air sitting above it. So it forces air out of a duct at the top and then violently sucks it back in. This creates a relentless contra-rotating airflow. Now, to harness energy from those uneven, bidirectional wave patterns, you can't just use a standard fan. You need a very special kind of turbine. And the answer to that problem lies in the unique physical geometry of the Wells axial-flow turbine. Notice how the blades are positioned perfectly perpendicular to the airflow. The entire setup is designed so that the rotor spins counterclockwise at a mind-bending 2,000 RPM, capturing energy no matter which way the air is forced through the duct. But the real magic? That's entirely in the shape of those blades. Section 2, Decoding NACA blade aerodynamics. Let's zoom right in and solve this paradox. The big secret to this unidirectional spinning is aerodynamic symmetry. Specifically, the engineers use what's called the NACA 0015 airfoil profile. This highly efficient, aerodynamically symmetrical shape is literally the answer to our mystery. Because it is perfectly symmetrical, it honestly doesn't matter if the ocean is quote-unquote inhaling or exhaling. The blade experiences a lift force that drives it forward either way. It minimizes drag and acts almost like a sailboat, catching wind from alternating sides. It's brilliant. Now, to survive this violent, non-stop push and pull, the geometry has to be absolutely precise. The turbine relies on 8 perpendicular blades, and each one is crafted with a strict 125mm cord length and a maximum thickness of exactly 15% of that length. Nestled perfectly between a base radius of 200mm and an external radius of 300mm, it's a remarkably sturdy configuration built specifically to handle those extreme ocean forces without tearing itself apart. Section 3, Computational Fluid Dynamics Modeling. Let's take this physical geometry and bring it into the digital world. To accurately predict how air is actually going to flow over these blades before ever building a physical prototype, engineers rely heavily on computational fluid dynamics. Here's a quick step-by-step look at that workflow. First, they create the precise CAD model geometry we just talked about. Second, they execute what's called mesh discretization. Third, they apply some seriously complex mathematical models like Rand's equations, which is basically a way for the computer to tame and calculate the sheer chaos of swirling turbulent air. And finally, they run the full CFD simulation. Let's talk about that mesh discretization stage for a second, because it's wild. The digital space around the blade is literally sliced into millions of tiny blocks, kind of like a massive 3D puzzle. Engineers often use regular hexagonal meshes here because this specific pattern acts as a super stable foundation for the incredibly heavy math they have to do, especially around the blade tips where the air gets violently turbulent. So, how many of these tiny blocks do you need? Well, engineers actually conduct a sensitivity study, comparing several different mesh configurations to find the perfect balance. And the magic number for our Wells turbine model? Exactly 1.242 million nodes. Just think about that. That is a massive amount of data points being calculated for every single second of airflow. Known in the study as Mesh-A, this specific configuration offered the perfect balance of acceptable analytical quality without completely overloading the supercomputers. All right, so with the mesh built, the actual simulation fires up. It's powered by some heavy-duty software tracking the 3D fluid flow. And to give you an idea of just how precise this modeling is, they even use a 10-second sinusoidal harmonic function, basically a mathematical loop, to perfectly mimic the real-life 10-second inhale-exhale rhythm of natural ocean waves hitting the system. Talk about attention to detail.
Section 4. Simulating pressure and velocity. Let's see what all that data actually tells us.
When we visualize the invisible forces acting on our blades, the pressure data reveals something absolutely fascinating. Notice how the highest pressure, those bright red and orange zones, consistently hits right at the leading edge of the blade, no matter what the flow coefficient is. And by the way, flow coefficient is just a fancy engineering term for measuring how fast the air is moving relative to the spinning blade. This high-pressure zone forms a stagnation point, where the air essentially stops dead, which is exactly something this specific NACA blade is built to absorb effortlessly. Now, when we switch gears and map the velocity, or the airspeed, a very clear pattern emerges. As the flow coefficient naturally increases, you can vividly see the high-speed red zones being pushed further and further downstream, trailing dramatically off the back of the blade. It's incredible to see the aerodynamics at work like this. We also have to track vorticity. This is basically a measure of how aggressively the air is swirling around. At lower flow coefficients, we see higher vorticity tightly clinging right to the upper end of the blade. But as that flow rate really ramps up, we start to see the creation of very distinct, sweeping turbulence wakes trailing far behind the blade structure. This is pure fluid dynamics in action. Finally, Section 5, Optimizing Wells Turbine Efficiency. Let's bring all this data together for the final verdict. So the data ultimately reveals a very strict operational sweet spot. As long as the airspeed, that flow coefficient we talked about, stays at a nice medium range between 0.15 and 0.35, the turbine operates beautifully. It catches the absolute perfect amount of lift, whether the wave is rising or falling in that oscillating water column. And here's the big number. The rigorous simulation proves that the Wells turbine achieves a maximum yield efficiency of 55%. Now, you might hear 55% and think, that doesn't sound huge. But to put that into perspective for you, in the world of renewable energy, taking wildly chaotic, totally unpredictable ocean waves and successfully capturing over half of that energy to generate steady mechanical power, that is a massive game-changing victory. But hey, as with all cutting-edge engineering, we do have to balance the success with some real-world challenges. The simulation also highlighted a few flaws. At very low flow rates, like when a wave is just starting to build up momentum, the turbine can actually experience negative torque. Basically, the aerodynamics start fighting against the rotation, causing unwanted vibrations that engineers have to carefully manage so the system doesn't stall out. Which brings us to our final thought for today. Cracking the code of the Wells turbine proves beyond a shadow of a doubt that sophisticated software can solve incredibly complex mechanical paradoxes. By simply modeling the invisible chaotic forces of air and water, we can optimize these designs before a single piece of metal is ever cut. It really leaves you wondering, doesn't it? As our computational fluid dynamic capabilities grow even more powerful, how else will these models unlock the limitless future of renewable ocean energy? Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll catch you next time.